Oh, hi everybody, and today we're cooking up a little acid-base properties of salts. So today's lesson we're going to look at as a standalone question, but it is going to pop its head up in our lesson on titrations as well. So let's have a look at how salts work. So usually salts appear in a neutralization reaction. So an acid plus a base, one-way arrow here, makes salt plus water. You've seen this before as part of a double displacement in grade 11, and you saw it when you did some acid-base chemistry in grade 11. So a really good example of that using just a typical strong acid strong base is HCl plus NaOH makes NaCl plus H2O. I've color coded the Cl and the Na because I want you to recognize that those are the two pieces contributed to the salt. So you'll notice that the acid gives the negative part, the Cl, and the base gives the positive part, the Na. So the salt is from both of those pieces. And again, I've just talked about that down here. Oh, weird things are happening. Here's an arrow. All right, so strong acids. We have 6 strong acids. You don't have to write these down again because you actually already have this written in a previous note. But what is very convenient is on page 803, you can actually find these very easily. They're the ones that instead of a number beside them, they have beside them the word very large. So there are 6 of them all together that have, instead of a number, the word very large, and that is telling us that you have one of the 6 strong acids. So the way this works, if you have a strong acid, they make weak ions, weak conjugate bases, and they will not hydrolyze with water. So basically, if you have a strong acid, the piece of the salt that comes from the strong acid doesn't do anything. But if you have a weak acid, the part of the salt from the weak acid is strong enough to actually keep reacting with the water, because remember, it's a salt and water solution. So if the salt was actually reactive with water, the reaction could keep going, and that's what we're going to look into today. Strong bases, just a reminder that our group 1, 2, and group 2 metals bonded with hydroxide, except for beryllium, those are my strong bases. Same applies. So if you have a strong base, it makes a weak conjugate acid, and so any salt that's made from a strong base won't react any further, but any salt that's made from a weak base will react with water. So in general, the positive ion, or positive part of the salt, comes from our base, and the negative part comes from the acid. We're not going to actually be able to see the acid and the base they come from, because all we're going to see in these problems are just the salt. So to figure out whether the acid and base are strong or not, to figure out the base, you're going to add just an OH to it, and to figure out the acid, you'll just add one H plus to it, and that'll tell you what acid and base it came from. Notice here I've highlighted the fact that we're going to add one H plus, and you've seen me talk about that before. Remember, H's are donated one at a time, so sometimes we look at something and it seems like, oh, it looks really familiar, I'm going to put the 2 H's in there because that's the acid I'm most comfortable with, but we only add one H at a time. So let's have a look at our first example. All the questions are going to look the same. It's just, will this salt be acidic, basic, or neutral? So the way this works is we start with an ionization reaction. So basically I'm going to take my MgI2 and I'm going to dissociate. I'm going to turn it into ion. So I'm basically uncrossing and I'm going to balance. So there's 1 Mg and 2 I's. So that's step 1. Then I'm going to consider where they come from. So remember that the base is the part with the positive ion. So this one comes from the base, and if I add the OH, that tells me which base it comes from. I'm going to do the same thing with the acid. So remember that the negative part comes from the acid. I add one H to it, so H plus I crossing over just makes that acid. Now I'm going to figure out whether these are strong or weak. So let's start with the Mg. MgOH, Mg is a second column metal, so it is going to be a strong base. Since it comes from a strong base, that means the ion here is weak, so we slash it. It means it cannot react further. Let's look at the acid now. The acid is HI. If I go back and I look at my 6 strong acids, HI is one of them. Remember, I can also find them on page 803. Look across for the Ka, and if it says very strong, same idea. It means it's strong. So since it comes from a strong acid, it tells me the ion is too weak to do anything. Since both of the ions can't react with water, basically it's going to just be a water solution with no further reaction. Therefore, this solution will be neutral overall. Let's try one that's a little more complicated. Same first step, so I want to know, will the solution of NH4NO3 be acidic, basic, or neutral? I'm going to start with my ionization equation. So I'm going to uncross and balance. NH4 plus NO3 1 minus. No balancing here, they're all 1 to 1 to 1. And now I add my OH to the positive one. So it comes from NH4OH. And I'm going to add my H to the negative one, HNO3. And now I figure out whether they are strong or weak. So NH4OH is not a group 1 or group 2 metal hydroxide, so this one is weak. That means that the ion that it's making is strong enough to do something, so I'm going to put a circle around it. Going over to the second one, HNO3 is one of my 6 strong acids. Because it's strong, we know that the ion that it makes is weak, so we're going to put a slash. Now that we've circled something, this means that something's actually going to happen. Anytime I circle something, it means it's actually going to be able to react with the water that it's sitting in. Remember, this is going to be part of a saltwater solution, so it can actually react with the salt. So if I circle it, I'm going to take it and I'm going to add it to the salt and see what happens. So in this case, NH4 plus is a little bit tricky to work with. It seems like because there's not an H in front, it would want to be the hydrogen ion acceptor. However, it has a positive charge, so if I tried to give it another H plus, 2 pluses repel each other. So this ion actually is the acid ion, and it's going to donate. So on the product side then, I'm going to go to NH3 and H3O plus. Now that I've done that, I should be able to answer the question, will it be acidic, basic, or neutral? This one, in fact, will be acidic. And the reason why is since we have H3O plus ions in solution. All right, next one. Let's try this one, same deal. I'm going to start with writing out my equation. This one is ammonium acetate. Same question as always, and I start the same way. So I'm just going to uncross and balance. So NH4 plus C2H3O2 minus. Now I'm going to figure out whether to circle and slash. So I'm going to add my OH. And I can do this straight away if I want to. We already saw this one last time. We know it's weak, which means NH4 plus gets a circle. We're going to add the H to my acetate ion, and this one is not one of my 6s, so this one is also weak, which means I'm also going to circle it. Just like the last example, anything I circle, I now react with water. Sorry, I didn't reinforce this. I think I drew it properly on the last slide, but when you react with water, because it's still not strong, these are weak compared to a strong acid or strong base, we're going to go into equilibrium territory here. So NH4 plus water will be in equilibrium with its ions, and same thing with the acetate ions and water. They'll also be in equilibrium. So the first one is the same as the last one, so this one's pretty easy. We can go ahead and do that one. We're going to slide our H plus over and become NH3 and H3O plus. And in the second example, we're going the other direction. So we're going to have an H plus coming over in this direction. And we're going to have an HC2H3O2 plus an OH minus. Now, can we answer the question, will this salt be acidic, basic, or neutral? Some of you might be saying, oh, it's acidic, it's got H3O+. Some of you might be saying it's basic, it's got OH-. Some of you might be saying it's neutral because both of them are there and they're going to cancel each other out. Neutral is probably the closest thing to the real answer, but unfortunately, it's not. So think about what has to be true in order to be neutral. You would have to have equal amounts of H3O plus and OH minus, but these are in equilibrium, and we know equilibriums never go 100% to product, which means unless we know how much H3O plus and OH minus there is, we don't know who's winning this competition. So if they're equal, they'll cancel, but if one has more than the other, it's going to either be acidic or basic. So do we have a way of figuring out how much ions we have at equilibrium? Of course we do. They're called Ks. So what I'm going to do now is I'm going to look up some K values. So this ingredient is acting like the acid, so I need its Ka. Kas are always easy to find. I'm just going to look them up on page 803. So from page 803, Ka of NH4 plus, which is my acid, is going to be 5.8 times 10 to the negative 10. All right, the second ingredient here, the C2H3O2 is accepting the H+, so this is my base, so I need the Kb of it. So my first task or attempt would be to go to the Kb table. Oh wow, it's not there. Huh, so weird. They're always there. We know how to do this though, because we learned how to do this in our last lesson. So if I don't have a Kb, I come over to the other side of the equilibrium and I find the conjugate acid. And this Ka I can now look up. And its value is 1.8 times 10 to the negative 5. Now, just like I did before in my last lesson, I can use the Ka to find the Kb. So let's do the math. So, from page 803, oops, that looks like a 5, Kb of C2H3O2 minus, when I do my math, is 5.6 times 10 to the negative 10. So very similar here. 5.8 times 10 to the negative 10, 5.6 times 10 to the negative 10. The H3O plus is slightly greater, so I would say, therefore acidic, since Ka is greater than Kb. And that is the final answer on that one. Our last example looks pretty simple, but there's a trick to it. Let's see if we can figure it out. Starts out the same way as always, so NaHCO3, uncross, and balance. Those are our two ions, perfect. Let's go through. So for here, I'm going to add my OH. NaOH is a strong, so I know that one's going to slash. HCO3 minus, I'm going to add one H to become H2CO3. And if I look at my acids, this one is actually a weak, which means I circle. So looks pretty easy so far. I know that anything I circle, I now make a reaction with water. So the question is, does anyone see why this is tricky yet? And it comes at this moment in time right here. When I do this one in class and I let you guys solve it before I show you the answer, it's amazing how some people will see it one way and some people will see it a different way. And by which way do I see it, I mean, how does HCO3 minus behave? Because it's amphoteric, which means it can behave as an acid and a base, and that's exactly what it's going to do simultaneously, and that's why this is tricky. So I have to do the reaction twice. Yikes. Okay, so I can make it act like an acid because it has an H+, and I can make it act like a base because it has a minus sign, and we know that an H in front and a minus sign in the back are those keys to figuring out whether we have an amphoteric substance. So let's finish the first reaction. So if I do the first reaction, it will become a CO3 2 minus plus H3O plus, and the second one will become an H2CO3 plus an OH minus. You'll notice that this is the same situation I just had. So unless I have equal amounts of H3O plus and OH minus, I won't have anything neutral here. And because they're in equilibrium, I don't know what part of this actually makes these ions. So I have to go to my Ks. The first one, and this is where it gets a little bit tricky, this is the acid, so I'm looking for the Ka of HCO3 minus. This is part of that polyprotic acid table, and so if we go down there, we're going to see multiple formulas, multiple Ks, but this is the second formula, which means I need to use the second K. So this is Ka2 that I'm using, and it is 4.7 times 10 to the negative 11. All right, let's go over to the basic half. Again, this is my base this time. So I need the Kb of HCO3 minus. I start with the terrible KB table, obviously not there because it's useless. So I'm going to go over to the conjugate. Here's the conjugate acid over here. And I'm going to look up the Ka for H2CO3. Again, this is a polyprotic acid, so it's down at the bottom of page 803, and there's multiple formulas, multiple Ks. H2CO3 is the first formula, therefore Ka1 is the Ka that I want to use here, and that is 4.5 times 10 to the negative 7. So I'm going to use the Ka to find the Kb. So I've done the math over here, 1 times 10 to the negative 14 divided by my 4.5 times 10 to the negative 7, and I get the value of 2.3 times 10 to the negative 8. Some calculators won't put it into scientific notation, so you might only see 2.2, something like that, I think, in this one, but not to worry. So again, can I answer my question? Well, Kb is greater than Ka this time, so yes, I can. So since Kb is greater than Ka, therefore this particular salt will end up being basic. So just going through the steps, because it's kind of helpful to sort of outline these and then use these steps when we're doing homework. The first is to write out the ionization equation. So remember, we're uncrossing and balancing. Then you're adding the OH to the positive ion to figure out the strength of the base. Then you're adding one H to the negative ion to determine the strength of the acid. Then you're going to circle and slash. Ions from weak acids and bases, those are the ones you're going to circle, will react with water. So you're going to write the equation out for the water. And then you have to use your Ka and Kb when you have both ions reacting with water, including your amphoteric ions. Remember, amphoteric are ones that have an H and a negative in them. And then you'll do a comparison. All right, so you should be in pretty good shape to tackle this homework. Let's hope it goes all right.